Hello. Here we'll look at the generalization of the formula for the sum of arithmetic progression. This generalization will give us the answer for the sum of squares of consecutive numbers. And I will start with a spoiler. I will just write down the answer. So if I take numbers from 1 to some stopping point n and compute their squares and then compute the sum, I can rewrite it just as an expression in n in a rather simple way. It will be the product of n itself of the next number n of twice n plus 1. I have to divide it all by 6. So that is going to be the answer, but rather than just starting from the answer and trying to prove it in the shortest possible way, I will look at a natural path leading to this. So the kind of idea, the initial idea will be very similar to the idea for triangular numbers for the sum of arithmetic progression by just looking at in sort of induction procedure, starting with and sort of a some expression for the cube of a number n. Start drawing the cube. So this cube facing us with its 3 sides, and suppose that it has the side n plus 1. And we can think of it as a build-up of unit cubes, and that is the number of them needed to construct this. And let's see what do we have to take out of this cube to get a smaller cube, the cube of size n. So one way of creating a smaller cube out of our given one is to take these 3 sides and shave them off, just one unit deep. So let me draw sort of this line of unit cells, which definitely will have to shave off, and yeah, there are some cubes in between. So these are just the corner cubes which we will have to delete, but as well we'll have to delete this face and this face and this face. And so looking first at the square faces, we have 3 of them, and each of them has side n, because one is taken already, so the number of unit cubes in them will be n squared each. And then what remains is this corner shape, and we have 3 equal pieces, not counting the corner cube, and they are just n units in length each. And then we have the leftover corner cube, which we'll have to take out as well. So that, of course, is the binomial formula. Just an example of it. But that is geometric interpretation, which is more or less easy to see. So I will do something to the first side unreasonable. I will rewrite the answer in terms not of n, not the answer, but this extra bit, the shaved bit. I will recompute it in terms of n plus 1. The reason is because I'm expanding n plus 1, I want to have the answer in the same quantity in n plus 1. So that will be 3n plus 1 squared without 3 copies of n plus 1, still plus 1. You can check that that is the same as this. You could check it by doing just straightforward algebra, opening the square, cancelling the terms and seeing that you end up with just this expression, which again counts the number of cubes which we'll have to remove. So that now is a procedure of taking a cube of a number and reducing it down to a cube of a previous number up to some extra bit. And we can start now with this number n and again reduce it by 1 and continue. So let's just try this next step. When we reduce n to n minus 1, we will have to write the extra bit coming from that reduction for n cubed, and it will be 3 copies of n squared minus 3 copies of n plus 1, and we already had this extra expression coming from shaving off the original shell. And the rest is, well, people call it induction, but really it's just a repetition. But that is an instance of induction, but done in reverse. And really, in most of the cases, induction is way easier when it is done in reverse. So if we continue doing that, if we continue decreasing this this number under the cube, we will keep adding more and more terms, but it will be terms of the same shape. So if I'll just write all of them, the first will be, the last really will be 1, and then I'll have the term when n is equal to 2, and then I will go all the way to my original terms. Not fitting it in one line, but yeah, you could see. So that is another way of representing the cube of a number. So I started with some number n plus 1 cubed, and then I have this answer for it. I will rewrite it in terms of number m. So m cubed is equal to, and I have the sum, I will write it compactly, the sum of terms which are of the same shape. 3 times the square of some number minus 3 times the number itself plus 1. And that number is, well, 1 here, the number k, the running parameter of my sum, running index. It's starting with k value 1. You could check that when k is 1, indeed you end up with 1. And then 2, and all the way up to that number under the cube, which is m in my case. So that's what we established doing this induction in reverse. And of course, as soon as we have the answer, we can prove it in a more formalic way using the kind of straightforward induction, which consists of 2 steps, checking this sequence of statements for all m's, checking for the first allowed, which is m equals 1, and of course, yeah, that is this bit. When m is equal to 1, on the left I have 1, on the right I have the sum from 1 to 1, which is just 1 summoned. When k is 1, 3 minus 3 plus 1 is equal to 1. So I have my base. And the induction step will consist in progressing from this statement valid for m to the next statement, which is to be for m plus 1. So I take m plus 1 and I just use, well, I will just use the binomial formula. I will use it in this form, so we'll have m cubed plus 3m plus 1 squared minus 3m plus 1 plus 1. So that's what we already checked here. And then I will use the induction assumption, according to which m cubed can be written as a sum. And the sum runs up to m. And then we have this extra bit, which is the same shape as our summons. And we can combine them into the longer sum. One step longer with the same expression for summons. So we have the sum going up to m, and then we have the one extra bit, which is the summand, generic summand for m plus 1. So that completes the induction proof of the same formula. And now finally we can use it to derive this answer for the sum of squares. So what we need to do is, okay, let's just go back to our n. Let's write n cubed as the sum of all these expressions in the running index k. And now break it according to the inner structure of the summand, break the sum. So we'll have three sums. One will be of k squared. That's, after all, what we need to write down as a product. And it will appear three times because each of the summands, each of the k squares, appears with coefficient 3. In a similar way, we'll have 3 times the sum of just plain k, which is the arithmetic progression. And the last bit, which we'll have to sum n times, is just constant 1. And taken n times, it will give us n. So now we can rewrite in a simpler form everything but what we want to evaluate. That we just keep unchanged because we don't know what it is yet. But this is 3 times arithmetic progression, which is n plus 1 over 2. And then we have extra bit of n. So rather than continuing, I'm sorry, I will have to cross it. I will now isolate this term which I want to find out about and write everything on the other side. So I had n cubed, but then I'm taking this to the other side. The signs change. And I want to write it as a product or a fraction, but in a multiplicative way, decomposed as much as possible. So I will make the common denominator, it's going to be 2 here, and then I will factor out n immediately because I can. And what I will be left with is, out of here I have n cubed, but I'm putting it under 2, so it will be twice n cubed, but I'm factoring n out, so it will be twice n squared. So here I already had this denominator, and I had 3n squared plus 3n. Alright, first 3n squared, but I'm factoring out n, so it will go down to 3n out of 3n squared. I also had 3n, and then I have another n, but over 2 it will become 2n. I'm sorry, I'm not changing the sign of this n, so it should be negative n. So okay, again, I had a 3n out of this product, and then I have negative 2n, and that comes down to n, but I'm factoring it out, so that's what I have. And the final push, simplifying this, is to factorize this quadratic. We can. Check this out. It is a product of n plus 1 and 2n plus 1, and it's still all over 2. So that product is just this quadratic. And the last push is to take this 3 and divide by it, and we end up with the answer. So that's it. More comes later.